Okay, here we go. 4.4 practice problems. Number one, we're going to be given a function m of x, and it's going to be equal to the quantity of x minus 3 to the third power. And so the first thing that we need to do is take a look at this thing and say, okay, well, based on what I've been given, my parent function is x to the third. And it's our duty to know that that's going to look something like this. And so we're going to look into our function and we're going to see what transformation is happening. We also know that our parent function has a vertex of 0, 0. And so in order for us to find our new vertex, we're going to say, hey, look, here's the only transformation that's happening. And in this particular transformation, it is telling me to go to the right 3 units. And so if I start at the origin or the vertex, which is 0, 0, and I go right 3 units, my new vertex is going to be 3, 0. And so since I have my new vertex, I can pick some x values. I'm putting my vertex in the center of this xy chart. I can pick some x values that are really close to 3. So let's pick the number 2 and let's pick the number 4. And then, of course, I'm going to put each of those into this, and I'm going to calculate. So I'm going to have 2 minus 3 cubed. Well, that's going to give me negative 1 cubed, which is negative 1. And so I will have the point 2, negative 1. And then I will stick the 4 in there, and I will calculate that. And so I will have 4 minus 3, which is a positive 1, and when I cube it, I get a positive 1. And so I'm able to draw my new graph by plotting these points that I have calculated. And in my mind, again, I need to know that it's going to look like this, but I'm picking it up and I'm scooching it to the right. So I will graph 2, negative 1. I will graph 3, 0, and I will graph 4, 1. Now here's the thing, with just having these 3 points, this sure does look like a straight line. Okay, and it's very tempting to just go straight line. But again, we said our parent function was the cube, and we know that that's supposed to look like this guy. So we have to make this look like that. So we're going to start at our new vertex, and we're going to go up on the right-hand side like this, and then we're going to go down on the left-hand side like this. And this is my final graph. And so some of the questions in Hawks, they're also going to ask you to find the domain and the range, so we might as well get used to doing that. And so we know from our previous studies that when we find the domain, we are looking at the x values. And so in this instance, our eyeballs are glued to this x-axis. And so these little arrows on the top and on the bottom indicate that this happens, or that this continues in this manner forever. Well, in addition to this line going up, it's slowly going to the right. In addition to this line going down, it's slowly going to the left. So in this particular instance, the domain of this guy is all reals. As far as our range goes, we're looking at just the y values. How far up and down? Well, again, these arrows indicate that they continue in this manner forever. How far up? All the way. How far down? All the way. And so how do we represent that? Well, it's negative to positive infinity or all reals. And so now I have graphed my new function using my parent function. I found its domain and its range, and now I'm done. Okay, so number 2 is going to be very similar. The problem is going to be f of x equals x plus 5 again cubed, just to get an idea of what this looks like. And so we again know that our parent function is x to the third, and we know that it's similar to this. And we also know that its vertex is 0, 0. Now we're going to look at the function that we've been given. This says x plus 5, and because this says plus 5, I know that I'm going left 5. And so if I start at 0, 0 and I scooch myself over to the left 5, then my new vertex is negative 5, 0. And so I can choose some values. I'll put negative 5, 0 in the middle because that's my new vertex. And I'm going to pick some values that are close to negative 5, so negative 6 and negative 4. And then, of course, I'm going to take each of those numbers and I'm going to plug them into my function. And I'm going to have negative 6 plus 5 cubed. That's going to give me negative 1 cubed, which is still negative 1. And then I will have negative 4 plus 5 cubed, which is going to give me positive 1 cubed, which is still a positive 1. And so now I have 3 points. And what am I going to do again? Well, I'm going to come over here, and I am going to graph these 3 points and make sure that my function looks like this when it's all said and done. So here are the points I'm going to graph. So negative 6, negative 1. Okay, maybe extend this a little bit. Negative 5, 0. 1, 2, 3, 4, 5. And then negative 4, 1. 1, 2, 3, 4, 1. Okay, and again, it's super easy to look at these 3 points and just be tempted to to make a to make a straight line through this. But again, we know that we cannot do that. And so we will kind of zoom it up like this, and we'll make it a little more curved. I kind of missed that one there. And there you go. And so what we've done is we've picked this guy up and we've moved him over to the left 5. And so again, we want to find the domain and the range. Well, in this particular case, they're both still all real numbers. And so we will just list that out. And there we have it. Done. Okay, so number 3. This is going to be the first one where we have several transformations happening. And so when you're given the problem, it's going to look like this. M of x equals negative 1. Oh, let me start this again. M of x equals negative 1 plus, and then I'm going to have 2, and then I'm going to have the absolute value of x minus 1. And so what's going to happen is you're going to look at this and you're going to say, wow, this looks a lot different than normal. You're right. Okay, typically the thing that contains our x comes first. So here's my advice. Take 2 seconds and rewrite the problem. This is one term. This is the second term. So we're going to have 2 absolute value x minus 1 minus 1. And then we don't have to look at this guy anymore because the way he's written is slightly confusing. And so now we're looking at this function. We know that our parent function, I'm going to abbreviate PF, we know that's the absolute value of x, and we know it should look like this in the shape of a V, and we know that its vertex is still 0, 0. And so now I need to look at my new function, and this little guy right here and this little guy right here, these are the transformations that are actually going to make this vertex move. And since this is a minus 1, this tells me right 1. Right 1. And since this is a minus 1 on the outside, this tells me down 1. And so if I'm at my vertex 0, 0, and I go down 1, right 1, then my new vertex is going to be positive 1, negative 1, because I've gone right 1 and down 1. And so what's going to happen now is I'm going to pick my x and my y chart. I'm going to say, okay, 1, negative 1 is my vertex. Let me pick the numbers that are close to 1, 0, and 2. And I'm going to take 0 and 2, and I'm going to plug them into this equation, and then I'm going to be able to graph. So I will have 2 times the absolute value of 0 minus 1, and then a minus 1. Well, I know that 0 minus 1 is negative 1. And so let's see. The absolute value of negative 1 is just 1. And 1 times 2 is 2. And 2 minus 1 is 1. And so the x value for this guy is 1. I'm going to do the same thing, but I'm going to put, I shouldn't have done that. I'm going to put this 2 into the absolute value brackets. So I'm going to have the number 2 times the absolute value of 2 minus 1 with a minus 1 on the outside. And then, of course, I know that the 2 minus 1 is just 1. And the absolute value of 1 is just 1. And so that's going to give me another 2 minus 1, 1. Whew, lots of 1s here. Okay, and so now I know in my mind this graph should be a V. And I also know that its new vertex is going to be 1, negative 1. So I will graph this thing, and I will take a look at my final answer, and I'll find its domain and range as well. Okay, so 0, 1, that's going to put me here on the y-axis. And then my vertex, which is actually 1, negative 1. So I go right 1, down 1, okay? And then my last point, 2, 1. So right 2, up 1. And again, I know it's supposed to be in the shape of a V. And so I will connect those points, and now my graph is done. I've graphed it. However, again, Hawks is going to ask you to find the domain and the range. And so when we find the domain, remember, we're looking at the x's to see how far left and right this thing goes. Well, since there are arrows, these continue forever. And so it's going to continue both left and right, which means that the domain is all reals. Now, when we talk about the range, this one's going to be the first one that we've graphed that looks different. The range is how far up and down, okay? Well, you can see that right here on this little line, which is going to be y is equal to negative 1, I don't have a graph beyond that. And so as far as my y values go, the lowest y value that I have in this problem is a negative 1. And then, of course, these arrows indicate that I'm going up forever, and so I'm going to infinity. And so now I have graphed it, I have found the domain and the range, and I'm totally done with this problem. Okay, so the next one that I want to show you, number 4, I picked this one specifically because it also looks a little different, and I don't want you guys to freak out when you see that these look different. So the problem is g of x is going to equal x squared over 3 and then a plus 3. Now, this is the first one where we have seen a fraction, so to speak, and so what we want to do is we want to get that fraction out of there. So really, we have learned in the past that if we have a variable and there's no coefficient in front, we know it's actually a 1. And we also know that between this 1 and this x squared is a multiplication dot. So what I'm going to be able to do is rewrite this problem, g of x, instead of having x squared over 3, technically speaking, I can pull this out as a fraction, 1/3. And then I know that if I were to multiply that by x squared, I would get what I had. And so really, this is just 1/3 x squared. And then, of course, this plus 3 over here isn't going to matter. And so now I don't really want to look at this guy because I don't like the way he looks. Okay, I want to look at this guy. And so what's going to happen is I'm going to find my parent function, and I'm going to say, oh, it's just x squared. And I know that an x squared is a parabola, so it's a U shape. It's going to look like this. I also know that its vertex is 0, 0. Okay, now, this is also the first problem where we have, this is the first problem where we have had a compression. And so when I look outside, or not outside, but when I look at my function, I see this guy being multiplied in the very front, and then I see this guy at the very end. There is no inside here. And so this front runner guy tells me that this is going to be a compression, okay? I look inside, but I don't have any inside, so I'm not going to move this left or right. But this big guy out here tells me that I'm going to go up 3. So this is a compression, C-O-M-P. And so what happens is if I'm not going left to right and I'm still at 0, 0 and I go up 3, then my new vertex is going to be 0, 3. And so in addition to compressing this thing, I'm going to pick this guy up and scooch him up 3 units. And so here's my new vertex. And so I can make my X and my Y chart. And let's see, I'm going to stick 0, 3 in as my vertex, and the numbers that I'm going to choose to plug in are going to be -1 and +1. And so then I will do that. I'll say, okay, well, 1/3 times 1 squared plus a big fat 3. And now because I have a fraction, my guess is you're probably reaching for your calculator, which I'm okay with. Okay, I got mine too. So what I'm going to do is I'm going to make sure that we can type this in correctly. And so what I'll do is let's turn this thing on so you can see it. Okay, I may have to move it around a little bit. Yeah, there we go. And so I will type 1/3, and I will put a 1 in there. I will square it, and then I'll put a +3. And this is going to give me 3.333 or 3 1/3. Now I'm okay if you leave it as a decimal here. That's fine. It'll help you to graph it a little bit better. So we'll put 3.33, 3 1/3. Okay. Then I have to put, oh, okay, hold on, wait. Put in the wrong spot. Let me get my white out. For some crazy reason, I did 1 first instead of -1, which is okay. And so I'll go back and I'll do the same thing, but I'll put a -1 in there, and you'll see what's going to happen, actually. So I will do the same thing on my calculator. I will do 1/3, and I'm going to multiply that by -1, which is going to be squared. And then I'm going to add 3 to that as well. And it's actually going to be the same thing. Okay, so I guess I didn't need my whiteout after all. So the same thing. And so now I'm ready to graph. And I know that it's going to look something like this. My new vertex is 0, 3. And I'm ready to go ahead and do that. And so here's my graph. Okay, we'll get this baby set up. And so the first point that I want to graph is -1, 3 1/3. So I go over to the -1. I'm going to go up 3 and then just a hair. I mean, just a hair. And then I'm going to graph the point 0, 3. So 0, 1, 2, 3. Okay, and you can see that there's just a slight elevation change there. And then lastly, I'm going to graph 1, 3 1/3. So again, just a teeny tiny bit. Now, I already know that this is supposed to be a parabola. And so this is going to be a much fatter parabola because I'm standing on the top and I'm pressing it down. Okay, and so I'm going to go ahead and just open it up both directions, and there I have it. Done. Final answer. Now, again, Hawks is going to be saying, okay, well, you can graph it. Let's find its domain and its range. And so again, when we look at the domain, we're wondering how far left and right this thing goes. Well, these arrows, again, are continuing upwards forever, but also to the right, continuing upward, but also to the left. So in this particular problem, the domain is all reals. Now, as far as the range goes, you have to keep in mind that the range is how far up and down. And remember, if you look at this, I don't have any graph down here below this line. And this happens to be where the y value is a +3. And so because of that, my range is going to be from 3 to infinity, because I only have a graph from 3 up. And so now I'm totally done. All right, I want to do one more where we have to talk about the transformations and graph this thing, and I want to make sure that we have a really good idea of what this looks like. So here we go. We're going to have f of x equals, there's going to be a negative sign, a square root symbol, underneath of that, I'm going to have x plus 4, and then out from it, I'm going to have plus 2. And so, of course, as always, we need to know our parent function. In this case, it's the square root of x. And we know that it looks like this. Okay, we said sometimes it kind of looks like, it reminds us of a dolphin jumping out of the water. And we also know that its vertex is 0, 0. We know all of that information. And so now we see this negative sign, and we see this plus 4, and we see this plus 2. Those are the transformations that are happening. This negative sign out front, since it's in the very front, this tells me that there is an x-axis reflection. In other words, we know that it's going to be opening downward somehow. This plus 4, since it's on the inside, is going to tell me to go left 4. And this plus 2, since it's on the outside, is going to tell me to go up 2. And so if I'm at my vertex, which happens to be 0, 0 of my parent function, and I go left 4, and then I go up 2, somewhere up here is my new vertex. And it happens to be at the point, so new vertex happens to be at the point negative 4, positive 2. So there's my new vertex. And so from this vertex, I am able to choose some x values. I'm going to put my vertex in the middle. Now, or actually, you know what? I'm not going to put it in the middle. I'm just going to put it at the top. I mentioned in our notes that when we are dealing with a square root, we don't pick our x values the same way. Okay, instead of just picking, negative 5, negative 3, because that's right around where negative 4 is, I got to pay really close attention to the whole thing that's right here. Whatever value I pick for x, I want it to easily make whatever's under this a perfect square. And so if I were to pick negative 3, let's say, if I put a negative 3 right here, and I said, okay, well, what is negative 3 plus 4? Turns out it's positive 1. Can I pick the square root of 1 easily? Yes, I can. And so I go ahead and I'll pick negative 3. And so I will say, all right, well, the opposite, and then I'm going to put a negative 3 here, plus 4, and I'll plus 2. The opposite sign is just going to come down. We said that negative 3 plus 4 is just 1. The square root of 1 is just 1, but the opposite is a negative 1, and when I add 2, I get the number 1. And so this point will be negative 3, positive 1. Okay, so what if I were to choose negative 2, let's say, because that's logically what comes next. But if I put a negative 2 right here, negative 2 plus 4 is positive 2. I don't know the square root of positive 2, so I don't want to pick a negative 2. Well, what if I picked a negative 1? Because again, that's what comes next. If I choose a negative 1, I put it right here. Negative 1 plus 4, well, that's 3. I don't know the square root of 3. I don't want that. So what if I chose a 0? If I put a 0 right here, what's 0 plus 4? Oh, it's 4. 4 is a perfect square. So let's go ahead and pick 0. And so then let's put that in and let's see what we get. So if I have the opposite of 0 plus 4 and then a plus 2, well, the opposite sign just comes down. I know 0 plus 4 is still 4, plus 2. The opposite sign comes down. The square root of 4 is just 2. And negative 2 plus positive 2 is the number 0. Okay, so I would also like to have one extra point just to make sure that I have a good idea of what this is going to look like. And so logically speaking, I would want to choose a 1 next. But if I put a 1 here, that gives me the square root of 5. I don't know it. So if I choose a 2, that would give me the square root of 6. I don't know that. So if I were to choose a 3, that would give me the square root of 7. I don't know that. If I chose a 4, that would give me the square root of, 8? I don't know that. So if I were finally to choose a 5, that would give me, when I add that up, that would give me the square root of 9, which I finally know. And so I'm going to let my last x value that I pick be a number 5. And so here I go. I'm going to have the opposite of, I'll put a 5 plus a 4 in there, plus a 2 on the outside. Opposite sign comes down, 5 plus 4 is 9, plus 2 comes down. Opposite sign comes down, square root of 9 is just 3, plus 2. And so when I add this, I get a negative 1. And so finally, now that I have 4 different points, that's going to be enough for me to actually graph this thing and see what's going on. And so I will do that. Here's my graph. 1, 2, 3, 4. Make sure we get plenty of space on this baby so that we can see what this looks like. Okay, so here I go. The first point, which is my vertex, is negative 4, 2. So 1, 2, 3, 4, and then up to 2. Okay, and then negative 3, 1. 1, 2, 3, 1. Okay, and then 0, 0. And then 5, negative 1. So 1, 2, 3, 4, 5, negative 1. Okay, now, this looks really weird, okay? But what we know is, let me get rid of this for just a second. That should not be there, really. We know that it already kind of looks weird, right? It's already just one teeny tiny piece. And so this teeny tiny piece, in addition to having been flipped down, it's also been moved around. And so when I get back to my graph, I know that this point is my vertex. This is the point where it actually starts. And so what's going to happen is I'm going to have to do the best that I can to draw that shape through these points. Okay, I'm not the best drawer by any means. That should be a little more, a little more smooth there. But anyway, it's going to look like this. And so what I've done now is I have the square root, and it has been reflected over the x-axis. It's been moved up 2, and it's been moved to the left 4. And so this is my final answer. And again, I know it doesn't look great, okay, but this is correct. Now the last thing that I'm going to want to do is find the domain and the range of this graph. And so again, the domain, when we talk about it, we're talking about how far left and right. Well, clearly you can see that it stops right here. It doesn't go any further left. And of course, this means forever to the right. And so my question is, let's see, this is what, -4? That was our -4 too. So the x value to the furthest left is a -4. And then, of course, we said, since this arrow is pointing, we know it's going to positive infinity. So there's my domain, -4 to infinity. Now, as far as the range goes, when we talk about the range, we're talking about the y values. And so here is my highest y point, which again is the point -4, 2. And so the highest y value that I have is a 2. And we know, since this is going to the right, it's also going down. Okay, and so how far down? Well, negative infinity. And so what's going to happen is the range of this thing, because we want our smallest number to come first, is going to be negative infinity to 2 with a bracket. And now we're done. Okay, now it's time to look at some functions and some equations and decide if they're odd, even, or neither, and what kind of symmetry they have. And so we will take a look. I think this is number 6. The question is, this thing that I'm about to write down, is it even, odd, or neither? And so what has to happen is we have to prove it mathematically. And so here's the function. R of x equals -2 times the cube root of x. And we know from our notes that if we're trying to find if it's odd, even, or neither, what we do is we take x and we replace it with -x. So that's going to be the first step. So we're going to rewrite this as -2 times the cube root of -x. And then once we do our replacing, so replace x with -x, we want to simplify. That might be spelled wrong, but you know what I'm trying to say. Okay, simplify. So here we go. We know there's a multiplication dot between these two. We know that we are allowed to take the cube root of a negative number. This guy is just going to be a nice, neat -2. If all I had was the cube root of -x, guess what? It's also a negative number. And so when I multiply a negative number times a negative number, that's going to give me a positive result. And so when I actually do the multiplication here, I'm going to get +2 cube root of x. And so when I do the simplification, whoops, I shouldn't have done that twice. When I do the simplification, this is what I end up with. Okay, this is what I started with. Now my question is, are these two exactly the same? The answer is no. Then I say, okay, well, are these two exact opposites of each other? And the answer to that is yes, they are opposites. Okay, this was -2 cube root of 3. This is +2 cube root of 3. And so we're going to write over here that these are opposites of each other. And because they are opposites of each other, that tells me that this is an odd function. And in the notes, we had mentioned all the O's stick together. And so this is an odd function, and that's all I need to write. And now I'm done. All right, let's take a look at another one. So again, I'm asking you, is this even, odd, or neither? And so the function that I have is g of x equals, I will have the absolute value of x divided by the number 4 and subtract a 3. And so again, the first thing that I'm going to do, since I'm asking you if it's even, odd, or neither, is replace x with a -x. And so I will do that. I'll have g of -x equals the absolute value of -x over 4 minus 3. And then, of course, I want to simplify. And so we know that when we take the absolute value of a negative number, it's positive. And so when I do my simplification, I'm going to get, hey, the absolute value of x is just the same as the absolute value, I got to back up. The absolute value of -x is actually the absolute value of x. Same exact number. And that's going to be over 4, and that's going to -3. And so here's where I ended. Here's where I began. They are exactly the same. So we're going to put, hey, guess what? They're the same. Okay? Maybe we even write exactly the same. Because of that, we know this is an even function. And that's my answer. And now I'm done with this particular problem. Okay, so number 8, in addition to asking you if it's even, odd, or neither, we have to talk about symmetry. And so some of the questions are going to ask you, does the problem that you're about to look at have x-axis symmetry, y-axis symmetry, origin symmetry, or none? Okay, and so what's going to have to happen is we're going to be given an equation or a function, and we're going to have to do the math, so to speak, so that we know what type of symmetry it actually has. And of course, when we looked at the graphs in our notes, it was really easy to visualize, but we know that that's not always going to be the case. Okay, you can't just say that Amanda said, you have to prove it. So here we go. Here is the in this case equation that I'm going to deal with, and I'm going to have 2x plus y squared equals -2. And so the question is, hey, if I put this thing on a graph, what kind of symmetry does it have? Well, remember, I gave you a hint, and I said, hey, guess what? When you see y squared, that tells me it's going to look something like this. Now, I'm not saying it's exactly that, but it's going to be similar-ish to that. Okay, and we know a couple of things. Because it doesn't pass the vertical line test, it's not a function. We know that. It's just an equation. Okay, and so we also know that this is the x-axis. And so by just looking at the graph, I can tell you right now that it has x-axis symmetry. Whoops, x-axis symmetry. And you can say, oh yeah, I'm done. But here's the thing. When you go to take the test, you have to prove it. And so in order for us to prove it, we're going to do something similar to the odd, even, or neither. We are going to take this y squared and replace it. So replace y with a -y. And if it's the same, bam, you've got your x-axis symmetry. So let's do that. So we're going to have 2x plus, instead of writing just regular y, I'm going to write -y. I'm going to square it. Of course, I want to simplify. And so 2x will stay the same, plus sign. Well, what happens when I have -y and I square it? Well, that just means -y times -y, which actually gives me a positive y squared. And of course, the -2 is not going to change. So here's where I ended. Here's where I started. They are exactly the same. And so because of that, x-axis symmetry. Done. And again, here's a picture of what that looks like. All right, number 9, we're still looking for symmetry. And so the problem that we're going to have is 2x minus y equals -2. Now, in this particular case, we're going to notice that y is not being squared. We're also going to notice that the x, no, let me back up. We're going to notice that the y is not squared. We're also noticing that the way this is written, it's just an equation. And so I'm just trying to figure out what type of symmetry that it might have. So what I like to do in this particular case is say, hey, you know what? When I just have regular y, we know this is a linear function because we have y equals, guess what? I just have x to the first power. Okay, it's a linear function. And so what you could do is you could say, oh, well, I can put this in slope-intercept form, and I could get that, you know, y is going to equal, let's see, I would subtract 2x and divide everything. So 2x plus 2. So what that means is we're going to have some type of a function. It's going to go up to, it's going to look like this. Basically, it's going to be a straight line, okay? And since it is not the line y is equal to x, which would look like this, there's not going to be any symmetry. And so this is an example of what it could look like when there is no symmetry. And so if you're just given a linear equation or a linear function, I guess I could put equation here, there's not going to be any symmetry unless it's a special one. And you're not really going to see any special ones. So anytime you just see x to the first power, you get pretty you get off the hook pretty easily by just saying, hey, guess what? That's a none. Okay. All right. Now I think this will probably be the last one that we do like this. We'll do number 10. And the problem, again, we're asking what type of symmetry we have. And so we're going to have y equals the absolute value of x. Well, again, what we're going to do on this one is we're going to replace x with a -x, okay? So we're going to have y equals the absolute value of -x. I need to simplify, and I know that the absolute value of x is just the absolute value of x. So this guy and this guy where I started, they're the same. And so we know from our odd, even, neither business that this is an even function, so to speak, or an even equation, I suppose. And because of that, we have y-axis symmetry. And a way to check yourself, you could say, hey, I already know what the absolute value of x looks like. It looks like this. And since this is the y-axis, bam, y-axis symmetry. Done. Actually, I want to pop back up to number 9 real quick. I want to show you the math on that one. I should have done that, not just the trick. So again, we were going to replace x with a -x, so that's going to give me 2 times -x minus y equals -2. And when I multiply, I'm going to get -2x minus y equals -2. And so we're going to look at this and we're going to say, okay, it's not exactly the same. So this is where I ended, and here's where I began. That's not exactly the same. It's not exactly opposite, and so that is why, mathematically speaking, that's how I know it doesn't have symmetry. So again, please, I forgot, really, please make sure that you're showing the math, not just saying, oh, well, I know what this looks like because you told me. All right, so now I want to move on to when we talk about increasing, decreasing, and constant, because those seem to be some of the issues that I see you guys struggling with. And so here's an example, number 11, let's say. Let's say that I have this line right here. This one's a good one because it gets you sometimes, okay? And so the question is going to say increasing, decreasing, and constant. And so you're going to look at this, and you're going to say, okay, as my eyeballs travel from left to right, okay, what's happening to this line? Is it going up or down, or is it staying the same? Well, obviously, we can see that it's not changing. It's a straight line. It's a straight horizontal line. So it's not increasing, it's not decreasing, and guess what? It's constant forever. And so when you are presented with an increasing, decreasing, or constant problem, I need you to make sure, please, that you give me some type of an answer. So if you want to write the word none, that's totally fine. But what I don't want you to do is leave it blank. Because if I see a test that looks like this, and I see something here, and I see these guys blank, in my mind, you've left it blank. Okay, maybe in your mind, you're like, oh, there's nothing there. So maybe put NA, draw a straight line, put the word none, do something so that I know that you know that you're not actually just leaving it blank. All right, let's look at another one with the increasing, decreasing, and constant. That was number 11. This will be number 12. And so I'll have this graph, and I'll have a few points out here, and it'll look like this. And so this is the absolute value. It's been x-axis reflected, and so there it is. And so my question is, where is it increasing, where is it decreasing, and where is it constant? Well, from just looking at this, we know it's not constant, ever. And so now here's where it gets real confusing for you guys sometimes. We don't care about the y-axis right now. All we care about is the x-axis. So all our eyeballs should be looking at is this right here, okay? Another thing that we need to realize is here's the vertex. And we talked about the vertex the other day and about how that is the point at which the graph changes directions. Another thing that we have to focus on are these arrows. Everybody thinks because these arrows continue means the line's going down. Okay, that is not what that means. What it means is this particular line continues in this manner forever. It just so happens to be pointing down. But if your eyeballs are right here on this line, and you're looking, if your eyeballs are right here on the x-axis, and as you look at the x-axis, what's actually happening to this line is actually, it's increasing. It's actually going up. And so when we get to the vertex, this is where it stops going up. And as your eyeballs continue to follow, this line actually does go down. Okay? And so what we're going to do is we're going to say, wow, where is it increasing from? Where is way over here? Well, way over here is negative infinity. And so as I scooch over from negative infinity, my line's going up, 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 up. Oh, it stops. What's the x point right here? This is where x is 3. And so in this particular problem, it's actually increasing from negative infinity to 3. And then once you pass 3 and you're heading towards positive infinity, it's actually going down. And so we're going to put the decreasing part is from 3 to infinity. And now we're done. That's it. We know we put our scratch line because there's no constant. Now, the other thing that I really want to remind you before I wrap this video up is when we're talking about increasing, decreasing, and constant, we're only ever going to use parentheses. Okay, we're not allowed to use brackets during this. Okay, it has to be parentheses. All right, I promise you this is the last one that I want to do, okay? And so what's going to happen is you're going to be given this function, and this time it's not a picture, okay? And we are still trying to decide where it's increasing, decreasing, or constant. Okay, so over here on the side, increasing, decreasing, constant. Now here's the thing, okay? I don't want us to have to go through all that rigmarole at the beginning and have to actually graph this thing. I don't want us to do that. I want us to just realize, hey, the parent function is absolute value of x, which looks like this. And because of this 5 that's on the inside, I know that my vertex is going to be moving. This guy right here, if I were plugging in points, he would have an effect. But for the time being, he doesn't affect the vertex, which is what I'm looking for. And so since I have this plus 5, this tells me that I have to go left 5. And so I'm going to pick up my picture and I'm going to scooch over to the left 5. So my new vertex is going to be negative 5, 0. So a rough draft, 1, 2, 3, 4, 5, looks like this. It's going to be opening downward since it is negative, but the 5 itself I don't really care about. So I know it's going to be looking like this. I don't really care how skinny or how fat it is because that is not going to affect my domain whatsoever. And so I can say, okay, well, here's what a rough draft of this looks like. And then I can say, well, hey, look, right here is where the graph changes directions. And I can cover these arrows up for a moment okay, with my fingers here, and I can say, look, as my eyeballs travel along this x-axis, this line's coming up. And then as I continue, this line starts to go down. And so I can easily see that it is increasing from negative infinity to that -5 with a parenthesis. And then when I get past that -5, all the way to positive infinity, it is decreasing. And of course, again, there is no constant. And so you will see a problem that is written out like this in HAWX. There will not be a picture to go with it. You will have to say, hey, you know what? This is what's changing. That's the only thing that's changing. And then, of course, hey, that's going to be flipped downward. And you just have to give me the new vertex and the fact that it's either up or down. And then bam, you can come right over here. You can find your increasing, decreasing, and constant. And now I am totally done. Thank you.